Last lecture we started discussing about an algorithm for deleting the node with the minimum key value from a Fibonacci heap. We have discussed about the major operations required in that algorithm. The first process that we discussed was to remove all the subtrees of the node to be deleted and insert them to the root list. That is the first step that we did. After that, removing the required root node, because all its subtrees are moved. Now you can just take out the node that you want to delete. And after doing it, we have done a procedure called consolidate, which do some rearrangements in the heap such that the resulting data structure will contain at most one tree of a given degree. So that is what we did, and we have to do few more operations to complete the deletion process, and that is the agenda for this lecture. We shall see what else is remaining to be done to complete the delete operation, and also we shall see the amortized cost of performing this operation. We will do a kind of aggregate analysis for obtaining the amortized cost of the deletion operation. So this is the algorithm that we started discussing, and till now what we did is, suppose we are given with a heap instance like this. First we deleted the minimum key node 3 and inserted all these 3 subtrees here in the root list. That is the first step that we did. Immediately after doing this, blindly we set h dot min as pointing to the next tree, which may not be correct. And after that we did what is called consolidation, where what we did is we obtained a set of trees such that there is at most one tree of a given degree. For example, here one tree of degree 1, one tree of degree 2 and one tree of degree 3, and we did it using a single dimensional array. We saw that the size of the required array is bounded by the maximum degree of a node in this tree. Now we need to form the root list. Actually the root list may not be correct. If we need to obtain a proper root list, and also we need to find which is the node to which h dot n can point. Given this instance it is 7, but in general how can you do it? So this process is the remaining thing that we have to do, which is called rebuilding the heap from the consolidated list of trees. It is just a consolidated list of trees. It is not a heap now, because you don't have h dot n, and the root list also may not be properly linked. By considering this as a running example, we can try to understand how can you rebuild the required heap instance from this consolidated list of trees. And what we can basically do is, you know that all these trees are collected in this array. So you can just start from this array at index 0, go all the way up to 3 in this particular case, in general up to the last element of this array, and what you do, you build a circular doubly linked list, and when you move along you try to find the minimum key value node and make h dot n pointing to that minimum key value node. It is just like finding the minimum from a sequence of elements. So here is that algorithm, remaining part of the algorithm, which I just copied from the textbook. And what it do first is it makes h dot min as nil. That means now the heap is made as an empty heap. You are going to collect that heap from the array. So now you are going to traverse this array starting from index 0. It goes all the way up to the maximum number of elements in the array. It is the maximum degree of the nodes in the heap. I hope you remember this notation from the previous lecture. Now you are checking, suppose array at index I is not nil, that means there is a tree pointed by that particular location. Then you are checking, if you have currently h dot min as nil, that means you are going to process the first tree. For example, in this case there is no tree pointed by the first cell, so you will come to index number 1, then you will find it non-nil. So what you can do is, this is the first tree that you are going to collect and add to the root list. So you don't have any other tree as of now, so you will naturally make h dot min pointing to that node, okay, and also you will create a circular doubly linked list, which is the root list containing only that tree, because you are going to collect other trees, but the first tree will be made as the only tree in the root list to begin with. Okay, that is what you do in this part of the algorithm. Else means you are coming to an index where there is a tree, but h dot min is not nil. Then what you have to do? Definitely you have to take that tree and insert it into the root list, and that is what you are doing here. Take that tree and add it to the root list, and then you have to see whether the newly added tree is having the minimum key value. The newly added tree is AI. Suppose its key value is less than the existing minimum key value, then you have to say that, okay, the new root is going to be the min, and that is what the algorithm is doing. Not difficult to understand what this part of the algorithm is doing, and if you apply this algorithm on this instance, you will get this as the heap instance. So this is a circular doubly linked list of root nodes of the trees, and the h dot min will point to 7. And with this the algorithm is over, and now we can try to do an amortized analysis to find the cost of this operation. That is, on an average case, if you perform a sequence of operations on the Fibonacci heap, then what would be the average cost of Fibonacci heap extract min operation? And this is the first 12 steps in the algorithm. There are 23 steps. So look at the first 12, and we can see that this is a loop. It goes for each child node of a node, right? So the complexity in the worst case is the maximum number of children, which is nothing but the maximum degree, okay, order of maximum degree. This is the notation for maximum degree. And you know that from a circular doubly linked list, the cost of deletion is order of 1. Easy to see that for this order of 1. Now we don't know what is actually the the cost for this operation, because we need to find the complexity of consolidate, that we will do later. Okay, so only when we obtain the time complexity for consolidate, we can determine what this is. And for the step number 11, no doubt it is order of 1. Okay, it remains us to find what is the time for consolidate. Till now it is order of the maximum degree, but consolidate is going to take a little more time. Later we can see. and you note that the number of trees in the resulting instance may be order of the original number of trees in the given heap instance plus the maximum degree. Why? Because suppose you are going to delete the min node and the min node is containing say these many child nodes or subtrees, then all those subtrees will be getting added to the root list. So after you perform this operation, you can see that this can be an upper bound on the number of trees. It is very important because in the consolidate procedure we need to use this for defining or finding the complexity of that operation. Okay, so the maximum number of trees after performing this part of the code could be the number of trees in the original heap plus all the trees which are added to the root list now, that is the subtrees of the not to be deleted are added, and in the worst case these many subtrees can be there. I hope you are getting me. And now you look at the consolidate procedure. Consolidate procedure, first step is this: you are creating an array. It is order of the degree, okay, maximum degree, because you go from 0 to that many cells. Now after that you are initializing all these cells to nil. Again, this is the complexity. Note that this is the notation representing the maximum degree of a node. Now you are performing some operation on a for loop. What is that you are doing here? For each node in the root list, and from the previous slide recall that in the worst case the number of nodes in the root list is upper bounded by T of h plus this quantity. So these many times the for loop may go, and if you look inside the for loop, only statement number 7 is another loop. It is a nested loop. Why inside 4? Every other statement executes only once. All other operations in the loop, for loop, except number 7 takes only order of one time. Now we need to find the number of times the while loop will go. Okay, and we can try to do an aggregate analysis on this. I hope you recall what is aggregate analysis. The example that we discussed was stack data structure, the stack data structure, right, where we found the complexity, the amortized cost of performing multi-pop as 1, and we argued it by taking into fact the number of push operations which is deciding a bound on the number of pop operation. If you perform a push operation pushing an element onto the stack, then you can only pop it once. You can pop it either as a single pop operation or as a multi-pop operation. So we found that multi-pop cannot take long time, or you cannot perform multi-pop always. Before doing that, you have to do a number of push operations. That is what we did that day. I hope you remember it. Even if you are not remembering it, that doesn't matter. We can try to understand what aggregate analysis we are going to do here. So we need to, if you blindly apply maybe like this into the maximum size of this array, which is again this quantity, right? That is the blind analysis, this multiplied by this. But we can prove that it is not going to take that much. This is the observation that will help us getting a tight bound on the complexity. Note that the Fibonacci heap link procedure, which is a sub procedure, actually removes a tree y from the root list and adds it as a subtree for x. So every time when you execute the while loop, the number of trees is decreased by 1, right? And hence, if k number of times while loop is executed, then the total number of trees to be considered is decreased by k. I hope you are getting, right? Because within the while loop, at statement 11, this process is actually removing the tree rooted at y from the root list and adding it as a subtree for x. So one tree is removed from the root list every time when the while is executed. So from the total number of trees to be processed, each execution of the while loop removes one tree. So if some 10 times the while loop is executed, 10 trees are removed from the root list. Okay, and hence you can easily find that the maximum number of times statements from 4 to 14 executed is only the number of trees in the root list, right? Only these many times, because if this while loop goes for k number of times, then k trees are taken out from this. So this quantity, then this for loop will not be executing for that trees. Okay, and hence using an aggregate analysis, we can see that the complexity of performing this in the actual case is upper bounded by the maximum number of trees in the root list. Okay, so this is the actual cost. So the actual cost is obtained in the worst case as T of h, which is the number of trees in the original instance plus the maximum degree. Okay, that is the actual cost. If you recall from the previous parts of the algorithm, everywhere it is either this quantity or this quantity. Okay, and so this is the maximum value, and so the actual complexity is upper bounded by T of h plus D of h of n, sorry, D of h dot n. And now we can find the amortized cost. Recall that the amortized cost of an operation is, here now we are going to apply the potential method to obtain this actual this observation. We have made an aggregate analysis, but for obtaining the time complexity of the operation in the amortized analysis, we are going to use potential method. And note that in the potential method, the amortized cost is defined as the actual cost plus potential difference, and hence we need to find the potential difference. By definition, we know that before performing the deletion, the potential is the number of trees in the original heap instance plus 2 into the number of marked nodes in the original instance. That is by definition. Now we have to see what will be the potential after the deletion operation. After the deletion operation, you know that in the worst case there can be these many trees, because we are collecting the trees in that array. In the array, the index varies from 0 to this quantity, 0 to this quantity, and so the number of trees is this quantity plus 1. If this quantity is 9, 0 to 9 means 10 trees are there. I hope you remember this. Then there is no increase in the number of marked nodes, because no mark is introduced by the procedure. Maybe there is a possibility of decreasing the number of marks, but there is no increase. So the maximum potential can be given as this. Okay. Now what is the potential difference? The difference between this quantity and this quantity. So the potential difference is nothing but the difference between this quantity can be verified exactly as this. I just copied this formula. this minus this is the potential before the operation. So you just perform the difference, you can see that this 2 mH and minus 2 mH are getting cancelled. So the quantity is easily verified as this. That is a maximum degree plus 1 minus the number of trees in the original instance. So that is the potential difference, and hence the amortized cost is the actual cost plus potential difference. This is the actual cost that we obtained from the previous slide, plus this is the potential difference that we obtained here. Okay. Now it can be easily seen that it is nothing but in the order of the maximum degree. So that is the time, amortized time for performing the Fibonacci heap extract min operation, and in a later class we shall prove that the maximum degree is in the order of log n. The maximum degree of a knot in a Fibonacci heap is order of log n. Assuming that this proof is done, now we can conclude that the amortized cost of performing the Fibonacci heap extract min operation is log n, where n is the number of knots in the Fibonacci heap. So today we finished our discussion on the algorithm for deleting the shortest key value knot from a Fibonacci heap. If you recall what we did, we know that H, the heap H will contain a field n pointing to the a field min pointing to the root of the tree which is containing the shortest key value. So it is directly knot, and here we have to delete that knot, and if that knot is not containing any subtrees, it is very easy, but in general there could be a number of subtrees. So what we did is removed all the subtrees from that knot and added them into the root list, and after that we removed the root knot which was safe. Then we did a consolidation procedure, and what it was doing is it just adjusted or moved knots from one tree to other or subtrees from one tree to the root list, so that the resulting data structure will contain at most one tree of a given degree. And after that we made a root list with all those trees, and then we found the minimum key value knot which can be pointed by the h dot min field, and that is the algorithm. And we have done a potential method of amortized analysis to find the time complexity of this algorithm, and which is obtained as log n, with an assumption that the maximum degree of a knot in a Fibonacci heap is bounded by log n. And for consolidation procedure we applied an aggregate method to obtain the actual complexity in the worst case as number of trees in the original instance plus the maximum degree, and that is the complexity that we obtained. And with this we are finishing this lecture. Thank you.